Hi guys, so this is our first lesson for the new unit, and this is going to just give you an overview of some of the main kind of questions or objectives that we'll have when we get into actual calculus. So I put that here on the first slide. Obviously, you can see all of our learning objectives for the lesson, but right here you can see this is kind of the two main points that we're going to start talking about today. We're not really going to get into that specific of how to do this, right? We have entire units based on these two questions. I mean, essentially the whole course is based on these questions. So this is just kind of give you a brief overview of what's happening here. Now, I want to stress, I know I didn't stress this for the first unit because it was just a review of what you did last school year, but essentially what I want you to start doing is when I post this lesson, you'll also see that I've posted the textbook pages. I want you to get a habit of starting to read them. I'm also going to start posting, not from our textbook, but PDF pages from a book that I'm reading to help me with learning how to teach this and how to learn it myself again, since I haven't done calculus in many years. I know it's going to sound silly, but it actually is very helpful. So I'm going to start posting pages from the book Calculus for Dummies. And essentially, this whole unit we're going to do is about limits. And so I want you to get into the habit of reading more for this class than you probably would have thought for a traditional math class. Okay, so I know it's going to be a little bit weird. I'm actually going to give you some time in class from time to time to actually, do some reading on your own. And as we get into the actual calculus, I'm also going to ask you to make sure you're logged into or kind of up to date on the AP Classroom for this course because I'm going to be assigning some assignments, and I'll mention them obviously in class. But once you guys get in the habit of making sure you're practicing some of these AP questions. Okay, so I'm sorry that was so long. Let's get to it. Now, a lot of this stuff is just going to be very theoretical to start. I'm going to do my best to lecture on it, but ultimately, like I said, I think reading about it will help you the most here. So we have three lines. You can see we have, one with a negative slope, one with a positive slope of 1/2, and another one that is actually a horizontal line, so it has no slope, y equals 2. And we're just taking a look at this idea of rate of change. And for lines, the idea of rate of change is just the slope, right? So as you're moving in the x direction, how far are you moving up and down in the y direction? So it's really not a big deal if every function that we dealt with was linear. But as you already know, we have a ton of functions that are not linear. So this next slide is showing you a quadratic function, all right? And it doesn't have a constant rate of change. So you can see if you move from left to right, remember, always read your graphs from left to right, that we actually are decreasing rapidly. Then we kind of decrease a little bit more slowly until we level off right at the origin. And then we get an uptick. So now we're increasing in the positive x values slowly at first, but then we start increasing pretty rapidly as we move farther into the right on our parabola. Okay, so the idea is, or the question that we have here is, when it's not a linear function, how do we measure the rate of change? So this leads us to that first kind of essential question of calculus, which is called the tangent problem. All right, and like I said, this is just a brief intro. We're not going to get into specifically what all this stuff means until a later unit, but just kind of previewing you what you're going to see in calculus. So we can approximate a rate of change for any function, right? Again, not linear functions. So any other type of function by looking at 2 points. All right, and if we draw a line through those 2 points, we can actually calculate the rate of change by calculating the slope of that line. This is called the secant line, and it's the one in orange that you're currently looking at. So you've been using the slope formula for many years, but that essentially is how we calculate the slope of this secant line. Okay, now here's the interesting thing. All right, the idea is that if we're approximating something called the tangent line, which we'll get to in a second, if we move that other point, in this case x comma f of x, the closer that point gets to the point we care about, the a comma f of a, the better or more accurate our approximation is for the rate of change for this function at that point a. Okay, so we'll talk about kind of sliding that point, and we'll actually do an activity on Desmos later on in the class. Not right now, but in the next maybe unit or two. we actually slide the point, you can see what happens to the slope of that secant line as it gets closer and closer to our point A. All right, so this leads us to something I mentioned called the line that is tangent to the function. So once that line x gets all the way to that point x gets all the way to that point A, we are now right on that they're the same. So essentially what we care about is we want to try to find the slope of that line that's tangent to the function f of x at a point A, all right? We'll get into later parts of calculus where we actually do this. And this really is something that is called a derivative. All right. And it's denoted with that notation f prime of A. That little x, or that little comma, I should say, after the f is f prime of A. So that means to find the derivative. Okay. And this whole idea of differential calculus, which we are going to cover, comes from this question. All right. So let's just start by doing some brief math here of looking at the same function, our quadratic function, f of x equals x squared, and we're trying to find the slope of the tangent line when our x is 1, okay? So I'll just do a brief sketch to help your brain here. So we have our curve, right, our parabola there. Here's our point 1, 1, and we're trying to find the slope of the line that's tangent to this function at that point. So essentially, we're trying to find the slope of this line in red. And again, this is just a brief intro, so we're going to get later into exactly how to do this and what this all means in later units. But essentially, for now, I just want to approximate that slope of the line in red using some other points on my curve. So we're going to start with a point that's 2, 4. So I'm going to find the slope of a secant line by using the change in y over the change in x. So that's going to be 4 minus 1 over 2 minus 1. So that's going to be 3 over 1, which is 3. So right now, we're saying that the slope of this line in red, all right, if I use the 0.24 to estimate the slope of the secant line, we're estimating the slope of the tangent line to be 3. Now, again, that is not the exact same line as the red line. If I zoom in, right, try to draw another sketch. If I zoom in on just the points 1, 1 and 2, 4, that's the line we just plotted. That's not the same line as the red line. Okay, the red line has a different slope. So we're essentially estimating the red line with the pink line. Now, if I keep going and move closer to 1, 1, so essentially doing the same process in part B, but now my point instead of 2, 4 is 3 halves, so 1.5 and 9 fourths. All right, so again, we're getting closer to the point 1, 1, but we're not actually there yet. So whatever this slope is should be a better approximation for our tangent line because it's closer to our point 1, 1. All right, so we have 9 fourths. You can use decimals if you want. Minus 1 over 3 halves. Minus 1, so 9 fourths minus 1, so that's 5 fourths. And then divided by 3 halves minus 1 is 1 half. Dividing by half is the same as multiplying by 2. So 5 fourths times 2 is going to be 10 fourths. And if you write that as a decimal, you get 2.5 or 2.5. All right, so if you compare 2.5 to 3, what we're saying is the slope of that red line, we're thinking is actually not going to be 3. It should be closer to 2.5. And again, as we get closer and closer and closer to 1, 1, we would get the exact slope of that tangent line. All right, so I'm thinking if I had to guess, we would think that it's probably going to be below 2.5. And you'll see later on in the next unit why we can actually confirm that it is, in fact, the slope is 2. Okay, let's keep going.